Hi people, this is torque, and torque is the ability of a force to rotate something. It is all about when you use a force to turn something around. Now, when a force moves something in a straight line, everything is pretty predictable. F equals ma, the bigger the force, the bigger the acceleration. That's pretty simple. The harder you hit something, the faster it ends up going. That makes complete sense. But when things start rotating, forces actually work in a slightly different way. They get a little bit more complicated. So this particular video is about the specific case of a force trying to turn something around. They start behaving a little bit differently. Let me give you a couple of examples here. Here's a door. Now, if you're going to push the door closed using the doorknob, it's going to be pretty easy to close it. It's going to swing that way and it's going to close. Most people would push the door by that edge, or they'd at least put their hand up there or down there and slam it closed. But if you tried to push the door there, or there, or there, right, using the same force, your same muscles, it would be much harder. The door would suddenly feel like it was a lot heavier than it actually is. It would be a much harder job to push this door closed from there. If you want to pause the video, just get up and try it now. Pick a nice door, open it up, and then try to close it with your fingers and your hands right near the hinges, right near the rotation point of the door. It's significantly more difficult, but it's still you. It's the same muscles that you have, and it's the same weight door. The door hasn't changed, you haven't changed, the force that you're applying hasn't changed. The only thing you've done is moved its point of application, and suddenly everything's different. Another example. A ship's wheel. Ship's wheels are big because it takes a lot of force to turn the wheel, and the reason for that is because the wheel is trying to turn a rudder that's underwater, and it's hard to get a big rudder to sort of move the water out of the way to rotate like that. Right? And so the wheel has to be big so that when whoever's driving the boat, whoever's doing the sailing, turns it, they can grab it way out here and turn it, and it's very easy. But can you imagine if you had to grab the wheel with your left hand there and your right hand there, and that was the only way that you could turn it, with your hands so close that you could touch your thumbs to each other? That would make it almost impossible to turn. Again, it's the same wheel turning the same rudder, and you've got the same muscles, but suddenly the job is more difficult. It matters where you apply the force. It turns out that when you're trying to turn something around, the further away from the point of rotation that you apply the force, the more effect the force has. If you apply it really close to the point of rotation, it'll work, but it won't work well. But the further out you go, the more effect the same force has. Right? Another example. Here's a guy trying to hold up a plank. He's doing a pretty good job so far. Excuse me. Now, if you let go of that plank, the point being made here is that if he lets go, that plank isn't going to drop like that. It's not going to fall straight down. It's going to rotate because the other end of the plank can't move. Right? It's leaning on something. So if he lets go of his end, it's going to rotate. It's going to do this. It's not going to do much of that circle. It's only going to go as far as the ground, but it's going to turn its way down. It's not going to fall straight. And for that reason, sorry, had to pause there. For that reason, if you put a weight on this plank, where you put it matters. If I added some weight to this plank and plonked it there, he's going to feel the weight, but he's not going to feel it particularly badly. Right? That's going to be felt, and he's going to have to work a little bit harder to hold it up, but not much. But if I put that same weight over here, I put it right next to him, all of a sudden he is bearing a much heavier load. It's far more difficult to hold that weight up. Right? So there are two things that matter in the case of torque. What matters is obviously how heavy the mass is. If there's more mass here, it's going to hurt. But also what matters is how far away from the point of rotation is that mass, or in this case, that force, that weight force being applied. And of course, this is physics, so there's a formula for this. And here it is. Torque equals radius times force. That's the symbol for torque. It's a Greek letter called tau. It's like a capital T with a bit of an identity crisis. Okay, don't worry about that too much. It's actually written in lowercase, so it's short. It's half the height of the capital F, for example. But that's what it looks like. I drew it big to make sure that you can see it fairly clearly. It's a letter called tau, but you don't need to know what it's called. You just need to know how to draw it. And it equals the force. Obviously, it's proportional to the force. If you double the weight on that guy's plank, it would double the amount of work that he would have to do to hold the plank up, etc. Right? So that makes complete sense. It's also proportional to the perpendicular radius. Now, I'll get to that perpendicular in a minute, but the radius, because this is all about things that are about to turn, the distance from the center of the rotation to the point at which the force is being applied is a radius. It's the radius of the circle through which this thing is going to be turned by the force. Right? And that's why we don't use the word distance. You use the specific word radius. Now, to tell you why it has to be a perpendicular radius and what that means, I'm going to have to use a diagram. So, not those. That one. Okay. So here's some object that can be turned. Right? Let's say that it has a certain mass and it's reasonably heavy and it takes a fair bit of force to turn it. Right? If I applied a force of 100 newtons right there, at 5 meters, it would turn. Right? So the torque in that case would be 5 meters times 100 newtons, which is 500. And the unit is Newton meters, Nm. That's all you have to do. There's no special new name for it. Newton meters. Excuse me. However, that is the perpendicular radius because the radius is perpendicular to the direction of the force. Right? That's the radius. That's the direction of the force. Right angle. Okay? Perpendicular. Easy enough. However, what if somebody didn't push this thing around by pushing it at exactly right angles? What if they pushed in a little bit? Right? Can be done. Let's try this again. The color coordinator, we'll do it in green. So somebody got a string on it and pulled it, but in this direction. Instead of pulling it straight up, where it would have been still perpendicular, they're pulling it in this direction. It would still work. Right? Obviously, if you pull something in that direction, it would still go around. The point is, that point that's being pulled isn't going to go that way. It's going to go that way. Right? It's stuck on the wheel. Right? The wheel is going to make it rotate in this direction, so it's going to go that way. And then it's going to start curving around and curving around. Right? So that's really not the full force that's going to be effective here. What you have to do is you have to find the component of this force in the direction that that point is actually going to move. And because this is always circular motion, the direction that it's going to move, that direction, is always at right angles to the radius of the circle. That's always going to be a tangent. That's always going to be a radius. The radius and the tangent of a circle, that circle there. Oh no. There you go. You've got it on camera. I've drawn a dodgy circle. It had to happen eventually. So anyway, the radius and the tangent are always at right angles, so that's going to be a right angle. However, if that's the 100, what number do you use for that? So we have to find the component of that force in this direction. And for that, I'm just going to scoot over here for a second. I'm going to make a triangle out of this. So there's the original force. And by the way, we can't do this without an angle, so I'm going to make up an angle. Let's say that that angle there is 40 degrees. Right, so there's the real force. That's the real 100 newtons. That's what's actually happening. This is the force that we're interested in. How much of that is pulling that spot in the direction that it's going to go? So we have to find what that number is. I'm going to close that off and make a right angle triangle here. This is how you do it. It's just using a bit of Pythagoras. Okay, so keep in mind when you make a triangle like this, the real force that's actually being pulled or being pushed or being used is always the hypotenuse of the triangle. And one of the other sides is the direction that you need to find it in, right? We know that 100 newtons is happening that way. We want to find out how much of it pulls the thing that way. So there's two sides of your right angle triangle. You know that that's the hypotenuse, so the right angle can't touch it. The right angle had to be over there. That makes the third side fairly easy to figure out. Having done this and knowing that that was 40 degrees. That's got to be 50. All right. This is where I'd keep telling you that you need to be very good at basic trigonometry to do physics. You don't have to be particularly good at much maths in physics. It's a lot less mathematical than people think from the outside looking in, but this you have to be very good at. Okay. That's the angle, that's the adjacent, that's the hypotenuse. This should be really easy for you guys now. Adjacent over hypotenuse is cos. The cos of 50 equals adjacent over hypotenuse. Therefore, that question mark is 100 cos 50. And that, whatever that answer comes to, is what the force is. I'll be back in a second having calculated it. 64.27. 64.27 newtons because it's a force. All right, so if you needed to find what torque was trying to pull this bar into a circular path, if you wanted to find what torque was trying to pull this bar into a circular path, the formula would be this. Torque equals, excuse me, 5 times that, 64.27 newtons. That's the effect of that 100 Newton force at right angles, right? So that perpendicular means the two things have to be at right angles. There is another way to do this. Instead of changing the force, you can change the radius, right? You can draw a different triangle to sort of shorten the 5. I personally think that's a little bit more difficult to do. I think it's more intuitive to figure out this triangle than a triangle that shortens the radius. But you'd end up with the same number. You would leave that as 100 and you'd have a shorter number here. And that would be shorter by a factor of cos of 50 as well. Turns out to be the same calculation, but it doesn't matter. Anyway, this comes to 32.135 Newton. In fact, sorry, I've got the decimal point in the wrong spot. It comes to, we can edit that out, this isn't live, 321.35 Newton meters. That, my friends, is the completely mistake-free version of torque. Bye-bye.